Okay, so this first question is about different types of radiation and how they would respond to an electric field. So since the beta is negatively charged, it's going to be attracted to the positive in the electric field, and the alpha particle is positively charged, so it's going to be attracted to the negative. The gamma has no charge whatsoever, so it just passes right on through. The beta particle is actually going to be traveling much further than the alpha particle will, as far as its path being skewed, because even though it's only got a -1 charge and the alpha particle has a +2 charge, you would expect the +2 charge to be able to pull harder, except this is about 7,200 times more massive. So since it's that much more massive, it's much more difficult to turn. It's got inertia, a lot more inertia that the beta particle doesn't have to overcome. Sort of a Porsche going around a corner and a dump truck going around a corner. Okay, let's do the next one. Gas-filled radiation detector. So in a gas-filled radiation detector, you've got some gas. It's usually argon gas. And then there's a wire, and that wire goes up to a battery. And then it goes to a counter, a little piece of electronic equipment that counts electrons as they go by. And then I've got the wire coming back. All right, so let's say I've got this argon atom sitting here, and big old punch of radiation comes at it. Bam, hits it. And then what ends up happening is that one of that argon's electrons pops off. So I got an electron here that's negatively charged. This argon is now positively charged. Now the reason that the electron doesn't go right back onto the argon, we would expect that since it's a noble gas, what ends up happening is, or the reason it doesn't, is because this wire right here has a positive 2,000 volts applied to it. So because it's so positive, the electron is attracted to it. And the exterior of the can is, let me erase that whole thing there. There we go. Is negative 2,000 volts. So the electron is pushed away from the can, but the argon itself is really attracted to the can, to the interior of it. So the electron hits this wire and it moves down the wire, it goes through the battery, and it gets counted +1, and then it goes through the wire here, and then what's waiting for it right here at the edge? Oh, it's a positively charged argon, where it reattaches itself, and then you just got regular old argon again. And it can happen over and over again. All right, let's go ahead and move on to the next one. And so we're going to do a half-life question. And this half-life question, the equation for that is half-life is equal to negative half-life divided by the natural log of 2 times natural log of final mass divided by initial mass. All right, so in this problem, our half-life is 22 minutes, so negative 22 minutes divided by the natural log of 2 quantity times natural log, and then my final mass is 1 gram and my initial mass is 66 grams. And so if I plug this into the calculator, I will get, calculator turn on for me, there we go. I will get negative 22 divided by the natural log of 2 times the natural log of 1 divided by 66, close, enter. And what I get is 133 minutes. All right, so if you wait 133 minutes, the 66 grams of lead-210 that's radioactive turns into 1 gram of lead-210. That's all that's left. All right, we're going to do the next problem. And the next problem has a different outcome. What we're looking for is how much is left after we wait a certain amount of time. In this case, I know how much I've got and how much I end with, and I want to know how long it takes. That's this problem. And this one right here is, I want to wait a certain amount of time, and I have this stuff, and I want to know how much is left when I'm done. Hopefully, the first thing that you notice is this is in minutes, and this is in hours. So let's just make this 180 minutes. That way the units will cancel out. So we're going to have to use this equation that we used before, but we're going to have to rearrange it, because this time, instead of looking for time, what we're looking for is N. We're looking for the actual final mass. So let's rearrange this equation. Time equals negative half-life divided by the natural log of 2 times natural log of final mass, original mass. So if I were to take this side here and multiply it by the natural log of 2 and divide it by negative half-life, let's do this. Stop moving. What'll end up happening is this will cancel with that, and that will cancel with that, and those guys are going to be gone. So I'll have to do that to the other side of the equation. So when I do that, I end up with time times the natural log of 2 divided by negative half-life. And that's going to be equal to ln NO. Okay, so now I need to get rid of this natural log, and I do that by taking e to the x of this side, and then the natural log cancels out. And I take e to the x of the other side, and what I end up with is e and negative time times the natural log of 2 divided by half-life is equal to n divided by NO. So now, if I multiply this side by NO, that cancels out, and this side by NO, what I end up with is n is equal to NOE negative time times the natural log of 2 divided by half-life. So let's plug our values in. So n is equal to 775 grams times E negative, and the time was 180 minutes, times the natural log of 2 divided by, not half-life. I want to actually put the half-life number in there, which in this case is 27 minutes. And if you punch this all into the calculator, I actually have this one done already, so I end up with 7.6 grams. It's grams because my minutes units canceled out, and the only unit I have left is grams. And that's what we were looking for anyway. How much will you have left? And so we're going to have 7.6 grams. And then the last thing for this is, what do I need for electricity? Well, you need a wire. That's easy enough. Say a coat hanger. And you need a magnet. All right, so think about like a horseshoe magnet, like one of these guys. It could be any kind of magnet, but think about one of those things. It'll be easy. And then I need relative motion between the two. All right, so this one's easy. I got a wire. This one's easy. I got a magnet. So what's this relative motion between the two? It means I can either hold the wire steady and take the magnet and move it back and forth across the wire, or I can hold the magnet steady and take the wire and run it in between the magnets. And that'll generate electricity. You could do this with a horseshoe magnet and a coat hanger at your house. It would work just fine. All right, that's it for homework 15.